light goes from air to glass, which is optically dense. By the way, being physically dense, D equals m over v, often relates to being optically dense, but it doesn't have to. Optically dense really means that the refractive index is high. Now, as the ray of light goes into the glass, it slows down, so it refracts towards the normal. Let's look at a ray that is going in at a larger angle. Still, it refracts towards the normal. Let's go further. Okay. Now, what if we go pretty much to 90 degrees? It may look odd, but we still get this refraction. But we can't go any further. We've hit the glass. Okay, so light travels the same route whichever way it goes, remember? So looking from inside, the ray turns away from the normal, away from the normal, away from the normal, and here, so far away from the normal that it pretty much goes along the surface. If I try to draw another one, it's not possible to refract. The light reflects. Not just along here near the surface, no. We know the rule for reflection, I equals R. So we get all the light reflecting, we get total internal reflection. Now this position here was the pivot, the turning point, the critical angle. If the angle of incidence was small, smaller than the critical angle, we got refraction and some partial reflection. If the angle of incidence was large, larger than the critical angle, we got total internal reflection only. And that's the definition for the critical angle. It's the angle at which behavior changes from total internal reflection to refraction plus partial reflection. So that's the definition. Let's turn to some maths. Refractive index was calculated using the ratio of the speed of light in air to the speed of light in the medium. Conveniently, this was also n equals sine I in air divided by sine R in the medium. At the critical angle, I, which is in air, is 90 degrees and R in the medium is C. So we get n equals sine 90 divided by sine C, which simplifies to n equals 1 over sine C, which is pretty handy for experiments.